Modern vision models map the physical world in a fraction of a second. They process video feeds and calculate depth, geometry, and camera positions instantly. A new paper from Oxford's Visual Geometry Group and Meta AI pushes this capability to its current limit. It's called VGGT-Ω, and it earned an oral presentation at CVPR 2026. VGGT-Ω is a feed-forward model. You pass it a folder of raw images or a video sequence, and it outputs a precise 3D point cloud along with estimated camera poses in a single mathematical pass. This directly challenges the industry standard for 3D mapping, classical structure from motion, or SfM pipelines like ColMap. Classical SfM relies on iterative optimization. It continually loops back to calculate and adjust thousands of individual data points to figure out exactly where a camera is in space. If you need a robot to navigate a room right now, a pipeline that takes minutes or hours to optimize will cause a crash. Replacing that slow optimization loop with a single-pass transformer is required to enable real-time spatial understanding for robotics and vision language action models. The central thesis of the VGGT-Ω paper is that 3D reconstruction models exhibit the exact same predictable, power law scaling behaviors as text and 2D image models. To test that thesis, the researchers set out to build a 3D vision model with a massive 10 billion parameters. We regularly see language models with tens or hundreds of billions of parameters. Why hasn't 3D vision scaled the same way? The bottleneck is memory. 3D dense prediction tasks consume catastrophic amounts of GPU VRAM. Pushing a standard vision architecture to 10 billion parameters simply exhausts available hardware memory before training even begins. To achieve language model scale in 3 dimensions, the research team had to completely tear down and rebuild the foundational vision transformer architecture. The teardown started with the original VGGT baseline architecture and its reliance on all-to-all global attention. In global attention, every image token communicates with every other image token across every frame. Mathematically, the memory required to compute these connections scales quadratically with image resolution, hitting a hard VRAM ceiling early on. This global attention matrix shows the actual token interaction within the model. The dark blue areas indicate that the vast majority of tokens are not exchanging meaningful information. The quadratic compute cost is being wasted on empty connections. The architectural fix is a mechanism called scene token attention, which utilizes a fixed set of registers. Instead of allowing every token to communicate freely, interframe information is strictly gated. Tokens can only exchange information by routing it through these centralized register nodes. By replacing the all-to-all attention layers with this mechanism, the researchers reduced the backbone's total floating point operations to just 6% of the original model. Destroying the global attention matrix eliminates the first major memory roadblock to a 10 billion parameter model. The second memory bottleneck sits in the decoding heads, specifically the dense prediction transformers, or DPTs. Standard DPT heads rely on high-resolution convolutional layers. While these layers don't add many parameters to the overall count, they require a disproportionate amount of VRAM just to store their intermediate activations during training. The team removed these heavy layers entirely, replacing them with lightweight multi-layer perceptrons paired with pixel shuffle operators. Pixel shuffle is an upsampling technique. It reshapes channel dimensions by unfolding directly into a spatial grid, allowing the model to increase resolution without executing heavy mathematical convolutions. The third efficiency hack targets the loss functions. Previous versions of VGGT used multiple dense heads to predict point maps, tracking features, and depth simultaneously, which drained memory. VGGT-Ω drops the redundant prediction heads and outputs only depth and camera parameters. However, the model is still supervised on those missing outputs during training through multitask losses applied to the simplified head. This keeps the accuracy high while lowering the hardware requirements. Combining scene token attention, pixel shuffle upsampling, and single head supervision cuts VRAM usage by 70%. This provided the memory headroom needed to use fully sharded data parallelism across multiple GPUs and train a 10 billion parameter model. Building a massive architecture is only the first step. A model this size requires millions of training sequences, or it will simply memorize the data and fail to generalize. Relying on static 3D environments limits capability. To map the physical world, the model must ingest dynamic video and predict complex, non-rigid motion. Gathering this data is difficult. Existing tools that generate pseudo-ground truth labels, like MegaSAM, frequently fail to extract accurate geometry when applied directly to raw, noisy video from the internet. To fix this, the team built a new, large-scale annotation pipeline. It forces raw video through 3 rigorous stages of filtering, discarding any sequence that fails geometric checks. In the final stage, modern image matching models verify the alignment, ensuring the resulting data is precise enough to act as a reliable training signal. The filtration was aggressive. Starting with 40 million internal internet-style videos, the pipeline kept only 0.8 million sequences. Combined with existing datasets, they finalized a training pool of 4 million highly precise environments. 1/3 of these 4 million sequences contained moving, dynamic content. This created a high-quality data pool 15 times larger than what was used for the original VGGT model. The supervised dataset pushed the model's capabilities, but to reach actual scale, the team developed a protocol to ingest 18 million completely unlabeled videos. They used a self-supervised teacher-student strategy inspired by Dino v3 architecture. Both models are fed the exact same video sequence, but the student model's data stream undergoes heavy stochastic augmentations, including randomized frame order permutations and color jittering. The student updates via gradient descent, analyzing distorted input to match the teacher's features. To prevent a feedback loop, the teacher ignores the training data, instead slowly receiving weight updates via an exponential moving average of the student's parameters. Running this distillation protocol required 128 H100 GPUs, operating in mixed precision over hundreds of thousands of iterations. By forcing the student to match the teacher despite severe data distortions, the model learns invariant spatial features. It deduces physical depth and camera position from raw pixels without needing human labels. This graph plots the result of scaling the architecture. The y-axis measures 3D point error, and the x-axis measures parameter count. As capacity grows to 10 billion parameters, error decreases steadily, proving 3D models scale like language models. This parameter scale translates directly to benchmark performance, specifically on complex dynamic datasets like Sintel. VGGT-Ω improved over the previous best camera estimation accuracy by 77% and achieved a 26% jump in depth estimation accuracy. Crucially, as a single-pass feed-forward model, it processes information 50 times faster than optimization methods that get bogged down recalculating positions on moving targets. This attention heat map demonstrates the qualitative output. The model accurately locks on to complex geometries and isolates specific objects in a single pass. Feed-forward architecture natively learns global spatial understanding, outperforming traditional iterative SfM on dynamic scenes. The model does face limitations. A 10 billion parameter model requires massive inference compute, preventing it from running on edge devices like mobile phones or lightweight drones. Additionally, the training pipeline still relies heavily on generating high-quality pseudo-ground truth data for initialization. But the first major takeaway is clear. 3D reconstruction models scale predictably with increased model capacity and training data. Second, reaching that scale requires an architectural redesign. Swapping global attention for scene tokens is the only way to bypass the VRAM wall. Finally, data remains the moat. Building a robust 3D model requires an aggressive filtering pipeline capable of isolating dynamic, real-world motion, backed by a self-supervised distillation loop to ingest millions of unlabeled videos. If you found this breakdown useful, please like and subscribe, and hit the notification bell to catch tomorrow's paper breakdown.